So let's go over the first web work. And the very first problem here, just compute this and then enter the number. Normally, web work can be your calculator, and I often encourage you to use that feature. So as an example, in problem 2 here, I typed -3 times 6, and when I hit submit, it knows that number is -18, okay? That will not work on this first problem. So if I show you, so like 3 and -3 is -9, and then let's see, I'll just do 6 minus 9 is -3, and there's another -20 happening. So, okay, I simplified a little bit, but I still want to use Webwork as a calculator. And now if I hit submit, doesn't like it. It's not expecting that character. So I have to actually go through and say, oh gosh, what's -9 times -23? It's the same thing as 9 times 23, and it's still not going to like that because it wants a number. So we'd have to enter it into, a calculator, or just do it. Let's see, 10 times 23 is 230, but we only have 9, so I should take away 23 from that. So that would get me 07. Sweet. So now hit submit, and there it is. Anyway, okay. Takeaway for problem 1. Webwork can be your calculator the majority of the time. Only in that very first problem, nose issues, is it not allowed. So that is the example here. Now, I also really want you all to be using exact notation whenever possible, because the 1 over the square root of 2 is not 0.7, right? And it's not, oh, it's going to do that. Okay, fine. Hit submit. It's not 0.707. Let's see if Webwork likes that. Okay, so it did like that to 3 decimal places. You never know how many decimal places you'll have to do because it's not always 3. Sometimes it's 4, sometimes it's 5. Sometimes I actually want the exact expression. So instead of doing this, what I recommend is to just type 1 over square root of 2. So SQRT, once I hit T here, boop, it becomes a square root symbol. So 1 over square root 2, that's one way you could enter it. Submit answer. And now it knows what you're talking about. So they were being nice when they let you enter 0.707. They can make it where you have to enter the exact expression. So, okay. And then other than that, it's just sort of getting used to typesetting. Webwork understands that when 2 things are next to one another, it's multiplication. So you can enter this, and it understands that you're trying to talk about that. All right. Finally, order of operations, it's something that, depending on your background, well, that's just a quick refresher. Parentheses come first. So the expression that's highlighted is 1 divided by 5 because the 2 plus 3 happens first. It's in parentheses. Whereas over here, it's not in parentheses, which means the division happens first. This is 1/2 plus 3, so you get 3/2. Okay, whatever. Let's go on to the next problem. Okay, evaluate this expression. We have some stuff. Again, I have faith that you can do it. Let's see if this is a time when we can just use it as a calculator. So I believe ABS. Yep, there we are. So ABS gets you the absolute value bars. You can also use these little things over here. Okay, so how do I click this one? I get absolute value. So 110 minus 258. And down here, I'm just going to take the absolute value. It's positive 28. Let's see if it likes that. Okay, it does. So see what I mean? If you just use it as your calculator, you don't have to go enter stuff somewhere else. You can just use Webwork. Okay, it's a huge benefit. Use it. Use it to your benefit. Okay, rules of exponents. So a lot of this, we're going to brush up on some older algebra. The power here is -5. And, well, it's negative because the thing is in the denominator. And it's 5 because the power is 5. Okay, we'll talk more about that in class. I love talking about power rules. I encourage you to think about it on your own time. Okay, which of the following expressions are equivalent to blah? All right, so we're definitely going to have a constant term because the 7 and the -4 is -28. And we're also going to have a linear term. That means something with just x to the power 1. We have +7 and -4. We're going to get +3x. And notice, so neither A or E, those aren't correct because A is missing a constant term and E is missing a linear term. So now we have to sift through all this. And point they're trying to make is different ways you can factor, right? So B is correct, because if you factor out x plus 7, then the first term is x and the second term is -4. So you'd have x plus 7 times x minus 4. Similarly, you could factor this second term, x minus 4, or just look, if you distribute the x minus 4, you're going to hit the 7, you're going to hit the x, right? So what's really going on in this problem, and look, I encourage you in all of your classes, not just mathematics, in all of your classes, ask yourself, what's the point of this problem? And you might see this and you might think, oh, okay, I can factor in this way. There's something going on here, which is they're trying to explain to you why you FOIL. That might sound weird, but like, it's because we distributed a binomial. So when you distribute, so here's your perspective. I don't know. This is my right side, but for you, it'd be it doesn't matter. Okay, so this is x minus 4, this is x plus 7. If x minus 4 hits the 7 and it hits the x, that's going to result in foiling. So that's the point of this problem. Remember to FOIL. All right. So what do we have here? Evaluate f at -3. So this is just, do we remember how to do functions and stuff? So -3 is the x value, and the y value is where f sends -3. And so unfortunately, we have to kind of zoom in and say, okay, -3, gosh, that looks like it could be this dashed line here. Hopefully that's -1. And I say hopefully because you always want to check the scale, right? So in this case, it is -1. But if instead of a -2 here, if that's a -20, then this would be -10, right? So always check the scale. Anyway, that's -1. Okay, so now we need to figure out when the y value is 2. So which x values does f send to a y value of 2? So I'm going to go to a y value of 2, and it hits here, x equals 0, and it hits here, at x equals -2. So your answer should be in the form blah, blah, blah. Okay, fine. So let's try that. X equals 0 and -2. Let's try that one. Doesn't like it. Can't convert a variable to a real number, blah, 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 blah. Okay, so maybe, maybe it wants this. Yeah, there we go. Sweet. Okay, cool. And you just witnessed one of the headaches of web work. I had the right answer. I had the right idea. And then syntax came and bit me in the butt, right? So this is one of the frustrating things about web work. This is why you should not put it off till the very end. And it's also why I make these videos. If you're stuck on a problem, I don't want homework to be a stressor. I want it to be a time of learning. And if you ask me, I think a stressed brain doesn't learn as well. So I have these lifelines for you. Maybe you're hitting your head because you're like, it's true. This is the way I would write it on paper. X is equal to 0, -2. Okay, but that's not the way the computer understands it. So, all right. Which of the following statements best describes the significance of this expression? All right, well, gosh, what the heck is f telling me? F of t denotes the number of people. Okay, so the number of people is the output. So that's the 19 here. Eating in a restaurant, t minutes after 5 p.m. So 3 minutes after 5 p.m., there's 19 people eating at the restaurant. Let's see. There are 19 people eating at, 5:03. Great, that's good. Which of the following statements best describes the significance of blah, blah, blah? All right, so A minutes after 5 p.m., there are 36 people eating at the restaurant. A minutes after 5 p.m., there are 36 people eating. Great, that looks good. Which of the following statements best, right, so same question. All right, so 36 minutes after, there's B many people. Let's see, 5:36, there are B people eating. That looks good. Which of the following? Yep. Okay, T minutes after, there's N many people. T hours? No, I want minutes. Every T? No, 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 no. In minutes? Nope. In hours? Nope. It's none of these. Okay, let's take a peek. Great. All right, on to the next one. All right, we got some tables, some fox populations, and some number of months. And T equals 0 means January 1st. T equals 1 means February 1st. Okay, always read the problem. Is T a function of F? Oh, so now we're getting to the math definition of function. Okay, what they're asking is if I told you a number in the F row, okay, because this is, okay, function of F. So that means F is your input. So I'm going to pretend I know a number in this bottom row here. And to be a function means if I give you one number in the bottom row, you can unambiguously give me the corresponding number in the top row. So All right, for example, if I give you the number 150, well, you're going to give me 0 because that's what corresponds to it. But if I give you the number 57, well, do you give me 5 or do you give me 7? What? This is not a function. Okay. What do I mean by this? Sorry, that was a bad. Avoid using the word this in mathematics because it might uncover some misunderstandings. I should have said t is not a function of f. I cannot go up. Okay. I can go down because if I give you any number 0 through 11, there is only one number assigned to it. And that's because none of these values up here repeat. Okay. So even if values down here repeat, so for example, if I give you 5, you give me 57. If I give you 7, you give me 57. It doesn't matter. That's okay. It's still unambiguous. But if I go up instead of down, now if I give you 57, you don't know whether to give me 5 or 7. Both of those could be paired with it. So anyway, going up is not a function. All right, let g of t equal f. So now we're going down. The input is t, so the input is this row, and then the output is f. The output is this row. Okay, g of t, note the Fox population in t months. Find all solutions to, okay, so when is the population 143? Well, month 1 and month 11. All right, 1, comma separate, 11. Let's see if it likes that. And it does. So see, notice how the syntax changed here on the last problem. We had to do comma, x equals and all that stuff. And here we don't. So problem specific, that's because, so Webwork is a free resource and different people from all around the world add to it. So who wrote the problem can dictate the syntax that they use. Sweet. So we left off on question 8, talking about domains. And let's hop over and talk about it. Of course, I just forgot what the question was. X minus 6, x minus 9. Got it. Sweet. So we have f of x. Wow, that isn't writing too well. One more time. Let's be a little better with our penmanship. F of x is the square root of x minus 6 over x minus 9. Which, just as a reminder, you can think of as x minus 6 over x minus 9 to the negative 1/2, although that won't really be useful, but whatever. Okay, so which x's are bad? Okay, so this is asking ourselves, which numbers can we plug in for x and we get an expression that doesn't make sense or isn't defined or whatever, okay? So for example, x equals 9, well, that's bad because it makes the denominator 0. And take any number you want. I'll just use 1, divide by 0. This thing here does not exist, okay? So if you plug in 9, you'll have something like 3 over 0. That also doesn't exist. So x is not allowed to equal 9. Okay, well, what else could happen? So, well, here's the thing. What's the square root of negative 1? And it's a semi-trick question because there's something really subtle happening here. And it does exist. It's called I. It's the number which has an unfortunate name of the imaginary unit. There's nothing imaginary about it. It's just however you currently think of numbers doesn't apply here. So if you think of numbers as like measuring lengths, that doesn't apply here. But if you think of numbers as like symmetries on a plane, that applies here. And if that confuses you, don't worry about it. Okay, but we don't want to allow that. We only want to have real numbers. Okay, that means we only want to have stuff that's on this number line here. And unfortunately, I lives up here. Okay, so I is not real, but all the numbers you know and love, those are real. So if you were going to take the square root of negative 1, okay, that's no good. In fact, the square root of any negative number, that's no good. So we need to figure out when this is negative. Okay, so how do you do that? Well, there's a sweet little trick. And I'm going to call this a sign chart. Okay. Sign as in positive or negative. The sign of a number is whether it's positive or negative. So let's mark off where 6 is and where 9 is on this number line. So this is a copy of the real number line R. And it does go on forever, whatever. Okay, so here's the deal. Pick any number you want that is in this region, so less than 6. So I'm going to pick 0. Okay, that's a good number. And if I plug in 0, what happens? I get a negative number up here and a negative number down here. The fact that I get -6 and -9 doesn't matter. What matters is that you have a negative number and a negative number. That will be true for everything less than 6. Pick any number you want less than 6. 5, plug in 5, you'll get a negative number. Plug in 5, you'll get a negative number, right? That's what's happening over here. So in fact, what number you use doesn't matter. What matters is that you'll have a negative divided by a negative. If I take a negative number and I divide it by a negative number, I get a positive number. So it turns out this region here, where x is less than 6, that is okay. All right, let's try this region here. So between 6 and 9. So I'm just going to plug in 7, for example, right? So if I plug in 7, then I have a positive on top and a negative on bottom. And a positive divided by a negative is negative. So, all right, we now know that we're negative in that region. Let me color it like this. Let's do this last region over here. It's okay. Yeah, it's the last region, but there are a few other things I have to check. Okay, so now something bigger than 9, I don't know, 1,000,000. If I plug in 1,000,000, this is positive and this is positive, so we're positive. Okay, so this part's good, where x is bigger than 9. This part is bad, where x is between 6 and 9. And this part's good, where x is less than 6. Okay, we know that x is not allowed to equal 9. Okay, so 9 is bad. Let's check 6. What happens when you plug in 6? Well, the top is 0 and the bottom is negative. The bottom being negative doesn't really matter because the top is 0, so you get 0. So it turns out 6 is okay. My cat just hopped on my lap and hopefully it doesn't interfere. Okay, great. Okay, so 6 is okay. So what did we just find out? We found out that based on this green region here, the stuff less than 6, that's okay. So x can be less than 6. But we also just checked x could equal 6, so x is less or equal to 6. Please don't walk on the keyboard. This is Hazel. She's adorable, and she will ruin all these videos. Okay, so x can be less or equal to 6, or it can be bigger than 9. X can be bigger than 9. All right, so let's hop back to Webwork. How do we enter that? So the domain wants interval notation using the U symbol. All right, fine. So the domain. So, oof, go away. Thank you. We can be from -infinity all the way up to 6. And we need a square bracket on the right-hand side here because we're allowed to equal 6. Okay. Or, so I'm just going to do capital U, and I think it accepts that. Okay, we'll find out. Or, don't you dare touch 9. So I do a curved bracket, right? Parenthesis. And otherwise, you can be anything bigger. So I can go all the way up to infinity. Another curved bracket. So let's just test that out, see if it understands. It does. Great. So this is saying less or equal to 6 or bigger than 9. All right, find the vertical asymptotes. Vertical asymptotes are when your function blows up, right? So a vertical asymptote, Hazel, you're friggin' killing me, girl. Okay. A vertical asymptote is when a function kind of blows up, right? So when does that happen? Well, one of the go-tos is when you divide by 0. So when this equals 0, so when x is 9, that's when this is going to blow up. And you can check, if you take 3 and you divide it by something really small, something that is close to 0, okay, then you're going to get something really big. And if you take the square root of something really big, it stays really big, okay? If you don't believe me, take the square root of 10 to the 20, you get 10 to the 10, which is still big. Okay, so anyway, it turns out the vertical asymptote is at x equals 9. Let's put that in here. And if this function has a horizontal asymptote, give its y value, there's no asymptote type 1. Okay, all right. So on the one hand, you could just graph this in Desmos, okay? You can find out all of this information. Now, a horizontal asymptote, that's a y value that your function approaches as x travels off to either infinity or negative infinity. So let's just ask ourselves, what happens as x gets really, really big, okay? Like huge. So think a billion, 10 billion, a million billion, okay? I would argue that if x gets really, really big, if you had $1 billion in savings and you spend 6, it doesn't really matter, right? This is for for huge, huge x, for all intents and purposes, taking away 6 or taking away 9 doesn't matter. So this expression looks like x over x. That's 1. That's 1. And the square root of 1 is still 1. So now we know our horizontal asymptotes. Do I have to say x equals or y equals type 1? All right, let's just see what happens if I enter 1. All right, submit. There we go. Sweet. All right, let's go to the next problem. All right, I've got a volume of a box, and it's made from a flat piece of material, 18 by 5, cut in equal sides. Great. Write down the volume as a function of x, doing to multiply out the factors. You got it. All right. So we have 18 by 5 to work with. So a piece of, sheet metal or cardboard or whatever. This is not drawn to scale. So here's 18, here's 5. All right. And then what we're going to do is we're going to cut out little squares. So this is x and x, x and x, x and x, and we're going to form a rectangle. And so then what's left over sort of looks like this. All right, my cat is young and she was weaned too young, and so she nurses on my t-shirt sometimes, and if you hear her, I'm sorry. Okay, so then we could fold up these sides and turn this into a box. Okay. Okay. So that's the process that we're doing. And this edge here, this x edge, that's the same as this, right? There used to be a square here, but we cut it out and threw it away. So in fact, this length, when you fold that up, is the same as these two vertical walls here. Sorry, that's both of these, whatever, they're all meeting. Okay, so all these vertical walls, those have size x. All right, let's do another one. This length here, this is what's left over when you remove, there used to be an x here and there used to be an x here. So this length is 5 minus 2 x's, right? I took away x on the bottom, I took away x on the top. So that's this length here, which is the same as this length here, but whatever. That's 5 minus 2 x's. And one more, this thing, which is this thing, well, it used to have an x and an x, right? And it used to be 18, but now it's 18 minus 2x. And so that's this longer edge here. All right, so what's the volume? It's x times, maybe here, we'll just do this, times 5 minus, is this minus? It is 2x, sweet, times 18 minus 2x, okay? And there's no need to multiply it out. It'll understand and accept it. There you go. All right, if we write down the domain of the box as an open interval, then what is A and what is B? Okay, so domain, we're asking what are all the valid numbers that x could be? What are all the valid x's? And you find it by figuring out what x is not allowed to be, okay? So is x allowed to be 20, is this feet or inches? What are we using here? This is inches, okay. Is x allowed to be 20 inches? I would say no, because in fact, this length isn't even, like, you don't have 20 inches to spare, right? No, okay. All right. Could x be 6 inches? No, because again, 5, right? So it definitely can't be bigger than 5. But also, if you have to cut out from both the top and the bottom kind of thing, like each corner, right? Then if you think about it, this distance here is the biggest x can be. It's halfway. That's half of 5, which is 2.5, okay? So that is the biggest x could be. What's the smallest x could be? And this is a bit of a trick question, because this is where we get to, okay, so 2.5 is how big x could be, okay? Could x equal 2.5? I don't know. We'd have to think about it. I don't think so. I think you would not get a box, okay? Because these two edges would come together. This is my other cat, Huey, and now we're just having a party up here. I'm never going to do this on my couch again, ever. Okay, so, right. This edge and this edge, the gap is 5 minus 2x. But if x is 2.5, or half of 5, there's no gap. So there's nothing to flap up and make a box. So I would say that you cannot be equal, okay? Similarly, it turns out the lower limit is 0, right? You can imagine these things sort of shrinking smaller and smaller and smaller. And at each time, each iteration, you get a box. It's like really shallow, really, really shallow, right? Because X is the, I don't know, height of your box. And so as X goes to 0, you just get a more and more shallow box, but you can make it as small as you want, theoretically. Okay, so that seems like that would work. So the lower bound I claim is 0, and the upper bound is 2.5. Let's give that a shot. Boom. All right, sweet. Next problem. Okay, function composition. This is a big deal, and I love it, and I'm not going to remember all this, so we're just going to do this whole thing. All right. So, what does f do to an input? F multiplies the input by 5, and then it adds 2, okay? So let's input the entire function g of x into f. So what is f of g of x? Well, f will take what you input, which is g of x, it'll multiply it by 5, and then it will add 2. So I'm going to take 5, and g of x is this, so 3x minus 10, and then I add 2. There it is. Exact same idea. You just switch them over here. So g of f of x is 3 times f of x minus 10. And that's 3 times, and I give myself parentheses because x, f of x is stuff happening. It's more than just one term. So 5x plus 2, boop, minus 10. All right, so there it is. Same idea for this one, just new functions. I'll do one of them, and we'll do this one here, okay? So big F of big G of x is, so what does big F want to do to an input? Well, it wants to cube the input and then add 1. And what is my input? It's the entire function g of x. So away. Oh, well, good enough. Okay. So g of x is x plus 3. That whole monster gets cubed, and then I add 1. Okay. So, all right, let's kill this, and we'll just enter them real time. This is more or less how I would do it. So I would say, well, what does f do? F takes 5 times the inside. What's the inside? It's g of x. G of x is 3x minus 10. Okay, and then I should add 2. Similarly down here, what does f do? Well, it cubes something, and then it adds 1. Okay, what's the something that it cubed? X plus 3, because that's g of x, right? So I'm just going to go ahead and submit those, and hopefully you see how to do the other two. Right? All right, the length of an, so now we're getting to why would we ever do this? Again, remember when I said you should ask stuff like, what do they want me to take away? It's a little harder here because this is just a rote skill problem. If you haven't heard that phrase, it's mindless. You do what you have to do. It's a computation, okay? When would you use function composition? So this is an example of when or why you might do that, okay? This is another, we're gonna have to screenshot this baddie. All right, you know what, let's do something different here. Let's zoom in a bit. There we go, and then screenshot it. Great. Sick. All right, so the length of an insect is a function of temperature. So if you know temperature, then there's a way to figure out the length, okay? And in fact, what that function is 9 plus the temperature divided by 10, okay? That's how you would go from temperature to length of an insect. The volume is a function of length. So now I can, if I know how long the insect is, I know how much volume it is. And the way I do that is I take its length and I cube it, and then I multiply by 8. Real quick, I just want to emphasize this is not 8L cubed. It's 8 times L cubed. And again, that's order of operations. Please excuse my dear Aunt Sally, PIMDOS, whatever. Exponents come before multiplication. So the fact that there's an exponent means it happens before we multiply by 8. Whereas here, parentheses come first. So you do the multiplication first, then you do the exponent. Okay. All right. Let's murder all of this. Great. Fantastic. All right. So now the temperature told us how long our bug was. How long our bug was told us how much volume the bug had. And the volume will tell us the mass. So now from here, I can figure out the mass of my bug, and it's 0.7 the volume. All right, great. So if I told you it was 20 degrees Celsius, can you figure out the mass of the insect? Well, yeah, what would you do? You would take 20, and I would have to divide it by 10, and then add 9. That's the length. But I want mass. Okay, so then I have to take this number here, which is the length. I have to cube it. So 9 plus 20 over 10 has to get cubed. And then I multiply by 8. This is the volume of my bug. Okay, and now I'm basically there to get the mass. I take the number I just computed and I multiply it by 0.7. Okay, 8, 9 plus 20 over 10 cubed. Boom. Okay. So look at all these. I took every step along the way, right? I began with temperature. I end with mass. What you're doing here is function composition. If I were to write this all out, the way you get m as a function of t is m is a function of v, which is a function of L, which is a function of t. Okay, and now this looks like what we saw previously, but just like really souped up. Okay, so let me justify it. Let me make it look the same. So what does m do? M takes your input and multiplies it by 0.7. So this would be 0.7 times v, which is a function of L, which is a function of t. 1, 2, 3. Great. Okay. And so that's 0.7 times. What does v do? Well, v cubes L and then multiplies by 8. So v is 8 times L of t cubed. Okay, and what does L do? Well, so I have 0.7 times 8, and this is a little bit, 0.7 times 8 is 0.56. So I'm just going to combine that. And then I have L. But L is what I want to know. So L was that 9 plus t over 10. And L is what gets cubed. Okay, so this here is the same as this here. If I just multiply the 0.7 and the 8, this will be 0.56 times 9 plus 20 over 10. Okay, the difference is here I left t as a variable. I didn't plug in 20, and here I plugged in 20. And so these are the two answers respectively. This is my answer for that, and this is my answer for that. Let's go ahead and enter it in. Delete. Thank you. All right. So what do? I take my temperature, 9 plus t over 10, and then I cube it, and pay attention to syntax. There we go. I cube it, and I would multiply this by 0.56, I think is what ended up happening in the end. Yes, that looks right. And okay, here's what I love about WebWork. Work smarter, not harder. So let's select all, copy, and paste. And let's just change this t to 20 because that's what it is. Yeah, I just said that's what I love about WebWork. And then here we are. Ridiculous. Okay, at least one is not right. Let's see. It did understand that. Do I have all my things correct? So v is L, and L, and 8 and 7. 8 times 7. Oh, it's 5.6. Sorry, 5.6. That's what happened. Okay, so right. I should have known. I should have done a little mental check. If you were watching this video and you knew that, why don't you speak up? No. Okay, sweet. So there we are. Sorry about that. All right, next problem. How many do we have, by the way? What are we looking at here? 18. Okay, where are we? We are at 12. Oof, okay, more of the same. So function composition is a really big deal, okay? We should be very fluent in it, and it shouldn't phase us at all. So let me show you why it shouldn't phase us, all right? So previously what I've been doing is I write out what the function f does, but everywhere I saw an x, I replace it with whatever is inside f. So in this case, it's g of x. So I would say g of x. That thing is going to get cubed, and then I'm going to add 1. And then I would replace whatever g of x is. I'd write that out explicitly. So here we are, okay? That technique totally works. It's totally fine. So, all right, great. That's that. Oh, and it looks like we'd have to actually work it all out. Maybe, maybe not. And again, smarter, not harder. So this is something that's going to have a third power. It's a cubic, and there's only one option with a cubic. So this had better be C, okay? Similarly, when you square G, so look, we could do this problem without actually knowing what any of these things mean, really. When you square G, you're going to get something that's quadratic. This one has to be A, but if you actually work it out, so the thing that's getting squared is G of X. The thing that's getting squared is G of X, right? I just plug in what G of X is. Okay, excuse me. Great. Here, I want to multiply the two functions. So g of x is x plus 1. That gets multiplied by x cubed plus 1. And if you work it all out, it's something with a fourth power. So this had better be b. And so then you know this is going to be d. And it looks the same as 2. So I guess cab d is what I'm looking to enter. But I'm just going to not bother entering them. I'm just going to go to the next problem. All right. So which of the statements is the inverse? Okay. So population million years, let's write something down. Here's the idea. If I tell you what year it is, t, then you can tell me a population. And the computation you have to do, multiplying, dividing, adding, exponentials, logs, I don't know, whatever you have to do, that computation, that's a verb. You're doing a thing. That verb is referred to as doing f. You are performing the function f. Okay, so f will take you from t as an input to the population as an output. Okay, now f inverse goes the other way. If I told you a population, if instead p was my input, can you tell me the year where that population occurred? That is the idea of doing f inverse. It's working backwards. Okay, so conversation in, okay, and this is where I should have slowed down and really read the problem. So P equals F of T is the population in millions. Population in millions. Okay, so that just means like P could be 2, but that means 2 million. Okay, in year T. All right, fine. So now if I go the opposite way, so if you tell me the population, I will tell you the year. Okay, mean of F inverse, the year T in which the population is P million. Okay, so the answer is D. That seems good. Let's delete it. Let's just, there you go. All right. Oh, so close, like 5 more. All right. So the inverse function is the thing that goes the other way, right? So C is a function of X. Also, we have a tendency to name things a bunch. There's no need to call this function G. You could just write C as a function of X, and then you never need the G, okay? But whatever, I digress. C is equal to 650 plus 40X, okay? So if you tell me X, then I can do this computation, and I can tell you C. If X is the input, I can tell you C, that's the output. Now, we want to switch that around. If I tell you C, can you tell me X? We'll just solve for X. That's all you got to do. So, okay, what should I do? I should take away 650, and then I should divide by 40, and that will get me X. Okay, maybe I should have gone a little bit slower. C minus 650 is equal to 40X. That's a multiplication, so we should use a division, and we get here. Okay, so now what am I doing to C? Well, I'm taking C, I am subtracting 650, and I kind of just let's just do this. Okay, right, cut it. I have a division, so I should have just given myself that originally, and this is divided by 40. Now I can submit. There you go. All right, so same idea of going backwards. We're really emphasizing what the inverse function is as an idea. It's solving for when something happened, sort of. So the GDP is given by some function, which you're calling G as a function of T. T is the number of years. That moved my page. Didn't want that. Since 1990, the units of G are billions of dollars. Match the following. Okay, so I guess I'll screenshot it. I should really scribble stuff down. It just makes it easier. All right, here's the idea. You tell me T. I do a computation whose name is G. And then that will tell me the billions of dollars for that given year of GDP. Okay, so G inverse goes the other way. So G inverse of 9873 is asking, okay, now this says years since. Okay, so the year, the actual year is 1990 plus T, right? Years since 1990. So if no years have gone by, we're talking about the year 1990. If 1 year goes by, we're talking about 1991. So the actual year is 1990 plus T, but T is how many years have gone by. Okay, that's that word since over here that's happening. Okay, so G inverse will tell me how many years since 1990 when the GDP was this many billions. So not that doesn't have a billion. That has billions. Okay, so how many years after 1990 it was when this yes, C. It looks like the answer is C. Okay, now G of 11 on the other hand is how many billions of dollars it was in 2001, because if you add 11 to 1990 you get 2001, and so that'll tell me how many billions of dollars. Okay, expected to be in 11 years. Wait, is this expectation? Units expression below. Okay, I think this is good. We'll just go ahead and double check it. So it's C and D. C. Stop. Okay, D. Submit. There you go. Final few. All right. What's the average rate of change? Okay, so now we got some more vocabulary happening here. All right, sometimes abbreviated as AROC, so average rate of change. So we got 2 points, and it's the slope between those 2 points. That's the average rate of change. Okay. Now, the fact that G is a line means we already know its slope. The answer is going to be 7. But just as a refresher, what we have to do is take the 2 y values. It doesn't matter who you take first and who you take second. You just need y1 and y2 and take the difference. But whatever order you go in, you need to stay in the same order on bottom. So now I take the x values. So paired with 34 is 4. So I put a 4 here, minus. Paired with negative 22 is negative 4. So negative 4. Okay. So if you work this out, you'd better get 7. I'm not going to do it. I hope you do. Okay. All right. The function G is blank on the interval blank. I don't know. Let's see what the options are. All right. So here, what's the answer? It should be 7. And increasing or decreasing. It's a line with positive slope. It's increasing, right? There you go. Next. All right. Now, this idea of average rate of change, it applies to more than just lines. So here we go. Now, G is my dashed and F is my solid graph. What is the average rate of change of F, okay, over the interval blah? So F, F, right? I curve U1 and over the interval. So I look at 2.2 and F is equal to this value, 2.9. I look at 8 and 8, F is equal to 0. So the average rate of change is the slope between these 2 dots here. So what's the slope? Well, my change in y, final minus initial, over my change in x, final minus initial. It's this. And you can just enter that into Webwork and it'll know, right? So don't sweat it. What's the average rate of change of G over this interval? G is a line. You just got to figure out the slope. And conveniently, right, we know these two numbers, so you should figure out that slope. Okay, let's just write it down. Final y value minus initial y value over final x value minus initial x value. So enter that in here. That should do it. There you go. Right. So average rate of change, this F graph, right? When we went from oh, I wish I could just like it doesn't matter. Okay. For question A, the average rate of change is just that slope. Average rate of change is saying like, well, on average, it went down this much. And that's different than how F actually moved, right? But it's kind of like a tortoise and the hare thing, but not really. You can imagine like if you took I-25 and you get to go really fast and then you hit some traffic and you slow down. Oh, and then you get speed up again. And then finally you're in Denver, right? Your speed was really fast. Oh, and then it was slower. Oh, and then it was fast again. Oh, and then you came to a stop because you got to your destination. That, you know, your speed is constantly changing. Or I guess see your distance and whatever. But if you look at how far you went and how long it took, that's like a change in y and a change in x. You get the average speed. And so a different car could just go at that same speed the entire time. And you're like fast, slow, fast, right? And you get to the same place. That's what's going on with average rate of change. All right. Computation. All right. All right. So I'm going to do one of these the way I would do it. All right. So let's give ourselves a division here. And f of 2 is what I'm going to put there. And f of 0 is what I'm going to put there. So what is f of 2? Well, let's just plug 2 into our function. 2 squared is 4. So 16 minus 4 is f of 2. What is f of 0? It's just 16 because 0 squared is 0. What is 2 minus 0? That's just 2. So this is how I would do it. And I wouldn't sweat it. And then, oh, conveniently, Webwork tells you what it reduces to. It reduces to -2. All right. Now, what else? Based on the graph sketch below, match each of the following. All right, great. So between 2 and 0, which of these lines is going between the x values of 2 and 0? So we got a few options. There's D, A, and E. Those are all going between 2 and 0, right? But now you also have to be touching the curve when x is 0 and when x is 2. And now there's only one option. It's D, right? D touches the curve. So D touches the curve when x is 0, and it touches the curve when x is 2. The other ones don't. A doesn't touch the curve when x is 0, and neither does E. Okay. All right. How do I get out of here? Oh, there we go. Great. Cool. So this is D. Similarly, let's touch the curve at 2 and 4, and that looks like it's C. Okay, C. And let's touch the curve at 4 and 0, and that looks like it's B. All right. There you go. So, all right, that's it. See you next time, and have a good one.